everyone. This is the second class on complex numbers. In this class, we will start with some properties of complex number. In the previous video, we have seen how the complex numbers are defined and what is the basic operations that we can do on complex numbers, like complex addition, complex multiplication, complex scalar multiplication. And also one thing we have seen, that is the powers of I. What are the different powers we can find for I? We have seen that every positive integer power can be divided by 4 and we will get some remainders after the division. And finally, if n is the power of I and if we get r as the remainder when n is divided by 4, then I to the power n will reduce to I to the power r. And there are 4 possible values of r, that is 0, 1, 2 and 3. So that is implying that we will get 4 different values for I to the power n. For r equals to 0, it should be 1. For I equals to 1, for r equals to 1, that should be I. For r equals to 2, that should be I minus 1, that is I square. And for r equals to 3, it will be minus I. So 1, minus 1, I, minus I, these are the 4 possible values of any positive integral power of I that we have seen in the last video. So in this video, we will start with the first property, that is called the modulus of a complex number. Okay, so here the space is very short. Let me clear the page. Okay, so we are first doing the modulus of a complex number. Suppose we are taking the complex number as z equals to x plus iy. So we can plot this number in the two-dimensional plane. Suppose this is the point x comma y, the corresponding coordinate of the point is x comma y, where x is this length in the x-axis and y is on the y-axis. So the modulus for this complex number z is denoted by this mod sign, and it is defined to be the distance that we can get by joining the origin to the point. So easily applying the Pythagoras theorem, we can easily find the expression for mod z, that is nothing but root over of x square plus y square. It also can be considered to be the distance between the point's origin and the preferred xy point. So you can easily see it is from the distance formula. One thing you see, it is the sum of two squares and the root of that, so it will be always some positive real number. Okay, so there are some properties of mod. The first one is that this mod z is always greater or equals to 0. The second property is that if you take the modulus of z1 plus z2, you can write it as it will be less or equals to mod of z1 plus mod of z2. Property 3, we can easily take modulus of z1 z2, the product, as mod z1 into mod z2. And the fourth property is that we can do the same thing for the divisions also. Mod of z1 by z2 can be written as mod z1 by mod z2. Some basic formulas that can be easily proved. If you are having any problem in proving this, you can comment me. You can write in the comment. I will help you to prove this. Okay. The next thing is the conjugate of a complex number. If z is taken to be any complex number in the form x plus iy, then in the same way as previous we can plot this number on the xy plane. So suppose this is the point xy corresponding to the number x plus iy. So then we can take the reflection of this point on x-axis, and that can be obtained here in the same distance, that is where xy is. And we know that this reflection can be defined to be x comma minus y, and this reflection point is called the conjugate of this complex number x plus iy, and this thing is denoted by z bar, and is defined to be the corresponding reflection image, that is x minus iy. Okay, so it's a very important thing. The conjugate of a complex number, it is geometrically it is the reflection of the point xy on the real axis, and it is defined to be x minus iy. So you observe that the sign of I is basically changing here. If it is x plus iy in the first expression, then it should be x minus iy in the conjugate, and if it is x minus iy in the first expression, then it should be x plus iy in the conjugate. So from this you can assume the first property, that is z bar of bar is again z. Second property is that if you take the conjugate of the sum of two complex numbers, that can be reduced to the sum of the conjugates. In the same way it will hold for difference also. The property 3 is that the product z1 z2, if you take the conjugate of this, it can be written as the conjugate of z1 into the conjugate of z2. And the fourth property is obviously just as the previous one, that is it cannot be written here. Let me come to the next page. Property 4 is that if you take the conjugate of the division, then you will get it as the ratio of the conjugates. So these are some simple properties regarding modulus and conjugate. Now see, some notes are there. Number 1, if you multiply z with its conjugate, you will get something like this. If you take z equals to x plus iy, you will get this product for z into z bar. Finally you will see it should be x square minus I square y square, and that can be written as x square plus y square, and x square plus y square also can be written as mod z square, so that you can write z bar to be equals to mod z square. It's a very important formula that we will apply while rationalizing complex numbers. Okay, number 2, you see, if you take the sum of z plus z bar, you will get x plus iy plus x minus iy. So iy will cancel out, and you will get 2x. That also can be written as 2 times the real part of z. So it's an important formula that z plus z bar is equals to 2 real z. Similarly, for the difference also you will get something. It is z minus z bar is equals to x plus iy minus x plus iy. So this time x will cancel out, and you will get 2iy. That can be written as 2 times I times imaginary z. So this is another form. So these 3 notes, remember, These are important, and this can be applicable to problems. Let us find the standard form of 1 by z, where z is some complex number x plus iy. So basically we are finding the inverse of a complex number, the multiplicative inverse. So if z is x plus iy, then we can write 1 by z as 1 by x plus iy. Now see, since we have to convert it into a standard form, that is the form a plus ib, so there should not be any imaginary number in the denominator. So to remove it, we will apply this relation z bar equals to mod z square. Since mod z square is a real number, so then we can say multiplying z with its conjugate, we will get some real number. So keeping that in mind, we are trying to do that here. We are multiplying by the conjugate of the denominator, so that in the denominator it becomes a real number. So we have to multiply it again in the numerator also. And after solving it, after simplifying, you will get something like x minus iy divided by x square plus y square, as it is the modulus, square of the modulus. So see, it is almost in the standard form. If you split it in two parts, you will get the actual standard form like this. 1 by z is equals to x by root over of no roots are there. It's x by x square plus y square plus I into minus y by x square plus y square. So this is the actual standard form of the complex number 1 by z, where z is equals to x plus iy. So in this way, you can make any convert any complex number a plus ib in the standard form. It can be the product of ratios, or there will be products in the both the numerator and denominator. So after simplifying, you have to convert the denominator into some real number by multiplying the denominator by its conjugate, just as we have done here. Okay, so these are the basic properties. We have another property that is called the argument. So let us come to that. So next we are coming to the argument of a complex number. This also can be called as the phase of a complex number. Some complex number z. The term is denoted by argz, or sometimes it's also called the amplitude. So in this way, for that we write it in short as ampz. Okay, so what we can do here, if you take the complex number z to be the number x plus iy, then we can plot this number in the two-dimensional plane. So suppose this is the point xy, then joining this point with the origin, we are getting some straight line like this, and then this straight line will make some angle with the positive direction of x-axis. This angle, if you take as theta, is called the argument or the amplitude or the phase of the complex number z. So our task is to find this angle theta. For that, we will draw the perpendicular from the point xy on the x-axis. So then, if you consider this modulus to be r, then we know that this length is called x and this length is y. So from this triangle, say OAP, we can see that x by r is equals to cos theta, and also y by r is equals to sine theta. Let me erase this. So y by r is equals to sine theta. So from this we can write x equals to r cos theta and y is equal to r sine theta. So every time we will assume any complex number as xy, and for x and y we will assume those values as for some theta, those will be r cos theta and r sine theta. And since r is the modulus, we can find it from the complex number, and then using these two relations we will find the angle theta, because x, y and r are known here. Depending on the two values cos theta and sine theta, we can also deduce what should be the quadrant in which theta is lying, that we can find. So from this information you can easily find the argument of a complex number. So let us see one example. Suppose we are taking the number z to be 1 plus I. So then we are actually finding argument of 1 plus I. So we can consider this 1 as r cos theta and the other one, that is the imaginary part, as r sine theta. Now first we will find the modulus, and you can easily see that it is nothing but 2. So basically we can write these equations like this. You better first find the modulus and then write. The real part 1 can be written as root 2 cos theta, and the imaginary part 1 can be written as root 2 sine theta. So from these two equations we can find the values of cos theta as 1 by root 2 and sine theta also as 1 by root 2. Now we know that this value happens for 45 degree in the first quadrant, and also see both the values are positive, so we can assume that theta is lying in the first quadrant. So from here we can write theta is nothing but it's pi by 4, and this is the argument of the complex number 1 plus I. That says if you plot this number in the two-dimensional plane, it will make an angle 45 degree with the positive direction of x-axis. Okay, so this is the idea of argument. So let me give another example that will clarify your doubts. Suppose we take this number 1 minus root 3 I. So first of all we will find the modulus, and that is 1 plus 3, that is 2. So we can write it here like this: 1 is equals to 2 cos theta and minus root 3, this is the imaginary part, is equals to 2 sine theta. So now see, cos theta can be found to be half and sine theta is minus root 3 by 2. So see, first of all these values appear for the value of theta as pi by 3, and see here cos theta is half and cos theta is positive and sine theta is negative, so we can assume that it is in the fourth quadrant. So since it is in the fourth quadrant, theta can be considered as 2 pi minus the value of theta in the first quadrant, that is pi by 3. So it should be 5 pi by 3. This is the argument or amplitude of this complex number 1 minus root 3I. Okay, so this is the topic argument. Now There is one step extension of this topic, argument of a complex number, that will come from these. So you see, for every complex number x plus iy with modulus r, we can get these two relations, x equals to r cos theta and y is equals to r sin theta. Now if we put it in the complex number z, then we can get z equals to x plus iy, that is equals to r cos theta plus I r sin theta. This value r we can take common and get r into cos theta plus I sin theta. See, this expression is wholly converted into r and theta, and this form is called the polar form of z, that is the complex number x plus iy. So every complex number x plus iy can be written in terms of its r and theta. This form is known as the polar form because these coordinates r and theta are known to be the polar coordinates. We have studied only one coordinate system, that is the Cartesian coordinate system, but other than that we have another system of coordinates that is called the polar coordinates, where these two informations are important, that are r and theta every point is making. So this information we get from here, and every complex number can be converted into the polar form. Now, to convert any complex number into its polar form, what we need? Here we can see we are using the value r, that is the modulus of the complex number, and theta, that is the argument of a complex number. So depending on that, sometimes it is also called the modulus argument form or the modulus amplitude form. So let us find the polar form of some complex number. For example, suppose we are taking the complex number this one, half plus root 3i by 2, that we will see later. It's called the complex number omega, or it is one of the complex cube roots of 1. So that we will see later. In this video, let us find the polar form of this complex number. So for this, first of all, we will find the mod. So see, the mod is coming like this: half square plus root 3 by 2 whole square, and that is coming as 1 by 4 plus 3 by 4, that is nothing but 1. So we have the modulus value. Next we find the argument of the amplitude. So suppose we have argument z as theta, then we can write the following: half is equals to cos theta and root 3 by 2 is equals to sin theta. See, both the values are positive, and it is half and root 3 by 2 for cos and sin. So easily from these we can write theta as pi by 3, as it is lying in the first quadrant. So we have both the values. So we can write the polar form for z as z equals to 1 into cos pi by 3 plus I sin pi by 3. The polar coordinates can be written as 1 comma pi by 3. So it's an easy thing. You just have to find the modulus and the argument of the complex number and write it in the proper form: r cos theta plus I sin theta. Now So next we come to something called the Euler's formula or the Euler's theorem. Leonhard Euler was a very eminent mathematician of his time, and due to him we get this following identity that is called the Euler's formula. It says the expression cos theta plus I sin theta can be considered as e to the power I theta. See, if this is true, then we can easily consider z from its polar form as r e to the power I theta, where r is the modulus of z and theta is the argument of z. And since we are getting something in terms of exponentials, it will be very helpful to calculate or to represent the complex number in this form. Because when you are multiplying two complex numbers, suppose you are having two complex numbers r1 e to the power I theta 1 and r2 e to the power I theta 2, then you are having the multiplication as z1 z2 is equals to r1 r2 e to the power I into theta 1 plus theta 2. Okay, let me write it in the next page. So suppose these two numbers you are having, then you can write the product z1 z2 as r1 r2 e to the power I into theta 1 plus theta 2. So the advantage is that you can easily calculate the argument of the product, and it says that argument of z1 z2 is nothing but theta 1 plus theta 2, that can be written also as argument of z1 plus argument of z2. So though these are becoming true, but this relation becomes false when you are considering the principal argument. That is something we will see later. It is not in our syllabus exactly, so we are excluding. For now, we are not going to that in discussion. But remember this relation argument z1 z2 is equals to argument z1 plus argument z2 will become false when you are considering the principal argument of the complex numbers. In the same way, you see, we can also write argument z1 by argument z2 is argument z1 minus argument z2, because when we are dividing, the exponential becomes subtracted. So for that we are getting this. So this is the thing that says the multiplications are some kind of rotations. Because see, suppose we are taking z1 as only e to the power I theta 1 for simplification, and z2 is equals to e to the power I theta 2. The modulus are 1 here. So if we draw these numbers in the two-dimensional plane, what we will see? Say this number here is z1. So if we join this with the origin, then we will get this angle as theta 1. And in the same way, suppose we are taking this number as z2, then we are getting this angle as theta 2. Now if we find the product z1 z2, you can easily see it is becoming e to the power I theta 1 plus theta 2. That means the product z1 will be somewhere here, where after theta 1 we are taking the angle theta 2 above it, and finally we are getting the angle theta 1 plus theta 2. So basically the line of theta 1 is rotated by an angle theta 2, and so we are getting the product z1 z2 with the argument theta 1 plus theta 2. So we can consider complex multiplication as a rotation uh, in the counterclockwise sense from the positive direction of x-axis. So this is the thing. This we can see from Euler's theorem, that is r e to the power I theta equals to cos theta plus I sin theta. Okay, so next let us consider one example that will show the equality of this argument z1 z2 equals to argument z1 plus argument z2. So suppose we are considering these two complex numbers. The first one is z1 is equals to 1 plus I, and z2 is simply I. So let us convert these two numbers in polar form first. So modulus of z1 is root 2, we can see, and the argument we have already found that argument z1 is pi by 4, and similarly the modulus of z2 here is 1, and the argument you will find to be pi by 2. So we can write z1 as root 2 e to the power I pi by 4, and argument, okay, let me write it in the proper form, that is cos pi by 4 plus I sin pi by 4. So now we multiply z1 and z2. See, it is I into 1 plus I. That means I plus I square. That means minus 1 plus I. Now if it is minus 1 plus I, then we can again find the modulus as root over of 1 plus 1, that is root 2, and the argument can be found as let us assume it to be theta. Then we can find minus 1 is equals to root 2 cos theta, and 1 is equals to root 2 sin theta. So from these two equations we can find cos theta is equals to minus 1 by root 2, and sin theta is equal to 1 by root 2. So cos is negative and sin is positive. That means we are in the second quadrant. So we can easily see that the value of cos theta, the value of theta is pi minus pi by 4, because in the second quadrant we consider the angles like this. So it is 3 pi by 4, we can see. So now you find argument z1 plus argument z2 is what? It is pi by 4 plus pi by 2. If you add this 2, you will get 3 pi by 4, which is the argument of z1 z2. So I think it is clear that when we are multiplying two complex numbers, basically we are rotating the numbers and adding their arguments. In the complex plane, you will see this situation like the number 1 plus I is here with real part as 1 and the imaginary part also as 1, and the number I is here. So when we are multiplying these two numbers, so you see this is the argument of the number that is pi by 4, and the argument of I is 90 degree. So when you are multiplying 1 plus I with I, you are getting the number minus 1 plus I, that is number here minus 1 comma 1. So the argument will be drawn like this. Now you see, after pi by 4, if you rotate 90 degree, you will come at this number. So basically this clears up the thing that while complex multiplication, we are basically adding the arguments. So pi by 4 plus pi by 2 is becoming the argument of minus 1 plus I, that is 3 pi by 4. Okay, so this is the the geometrical significance of complex multiplication, and it is through the Eulers theorem. And this also leads to something very beautiful that is considered as the most beautiful equation in mathematics. Let us see that. So we have already seen that Eulers theorem says e to the power I theta is equals to cos theta plus I sin theta. Now if you put theta equals to pi, what we will get? We will get e to the power I pi is equals to cos pi plus I sin pi. Now see, we know that sin pi is 0 and cos pi is minus 1. So we are getting this value, e to the power I pi is equals to minus 1. From this we can say e to the power I pi plus 1 is equals to 0. So this equation is very important, and it's considered to be the most beautiful equation in mathematics. Why? Because we are having two most important irrational numbers, that are e and pi. It is very difficult to prove that these numbers are irrational, and it will take a couple of pages to prove it. Next we have the famous number I, that is considered as the unit complex number or unit imaginary number which is important. Next, then we are getting the additive identity 0. We are also having the multiplicative identity, that is 1, and the most standard operation in mathematics, that is addition. So lots of rich things are there in this equation. That's why it is considered as the most beautiful equation in mathematics. Okay, so this is the thing that I wanted to discuss here. It's a beautiful thing, and our next topic will be the square root of a complex number. So let us see that. So suppose we are taking some number a plus ib, and we want to take the square root of this. We have already seen in terms of reals the square roots are not so good, because we cannot find the before this video we cannot find the square root of the negative numbers. And also we can say now that the square root of the negative numbers are not real. So what is the case for the square root of imaginary numbers or the complex numbers? So let us find whether it is true. It is the square root function is complete in the set of complex number or not. So suppose we are taking this number as x plus iy, then what we will get? If it is complete, then we can get the square root as also x plus iy. Now let us see after simplification whether we are getting something useful or not. So after squaring both sides, we will get a plus ib as x plus iy whole square. That can be considered as x square minus y square plus 2ixy. So what we can do from here, we can compare both the sides and we can write a is equals to x square minus y square and b is equals to 2xy. From these two equations, simplifying, we can find the values of x and y in terms of a and b. And since a and b are given, we are done with the thing. So how we can solve this, how we can find the values of x and y from these equations? For example, we can take the value of x as b by 2y, or you can take the value of y as b by 2x, and you can put this thing in this equation. So you can write a is equal to b by 2y whole square minus y square. So this will come as an equation of y or y square, whatever. You can find the value of y square from that, and then you can find the value of y also. So with that value, you can put it here, and you can also find the value of x. So we are done. We can find the values of x and y in terms of a and b from these equations. So we can find the square root of any complex number in terms of x plus iy. So let us see an example. Suppose we are finding the square root of 1 plus I. Then we can take root over of 1 plus I as x plus iy, and from that we can consider 1 plus I as x square minus y square plus 2ixy. So this is saying that 1 is equals to x square minus y square and 1 is equals to 2xy. So one way you can take the value of y, let me take the value of y here as 1 by 2x, and you can put it here in the equation. So from the equation you are getting 1 is equal to x square minus 1 by 4x square. So what you are getting here is 4x to the power 4 minus 4x square minus 1 is equals to 0. So to solve this equation, let us see what we can do. We can write it like this: 4x square plus 1 is equals to 2. Then we can write this equation as 2x square minus 1 whole square is equals to 2, and then taking the square root, we can write 2x square minus 1 is equals to plus minus root 2. So x square is plus minus root 2 minus 1 by 2. Now see, x is a real number, so x square cannot be negative. So the only possibility in this case should be x square equals to root 2 minus 1 by 2. The negative sign here is avoided because this will give a negative number in the square form, which is not possible. So from here we can get the value of x as root over of root 2 minus 1 by 2, and putting it in the value of y, we can write it like this: y is equals to 1 by 2x, that means 1 by 2 into root over of 2 minus 1 by 2 here. Sorry, it will be root 2. So it can be written as 1 by 2 root 2 minus 2. Okay, sorry, there is a silly mistake here. So from this equation we will get this as plus 2 plus 1. Here it is also plus 1. Here it is plus 1. And in this page it is plus 1 plus 1. So this we will obtain, and finally we can write the number x plus iy as root over of root 2 plus 1 by 2 plus I into the value of y, that is root over of 2 root 2 plus 2. So this is our square root for the complex number 1 plus I that we can do easily. So then we can say that root over of 1 plus I is this number. Root over of root 2 plus 1 by 2 plus I into 1 by root over of 2 root 2 plus 2. Okay, so with this we are finishing this video here, and we will see the cube roots of unity in the next video, and some problems we will solve in the next video. So for this video we are finishing it here, and thank you for watching.